So we also have a delta connection that we can make. Now, while it is possible to put your power supplies in a delta configuration, that's typically not done for various reasons. It actually, you can have slight variations in your power and you suddenly get an unbalanced system. So that's not typically done. But your loads can be connected to your power in a delta configuration. So your power is still in a Y configuration. So we still have our A, B, C, and our neutral here. So we still have that, but then our load here is in what's called a delta connection, and you'll be able to see immediately why we call it a delta connection. And again, we're assuming balanced, so these are all ZP. This here is capital A, capital B, capital C, and when you connect this, you're still going to do the A to A, the B to B, and the C to C. Now, one thing we should notice is that there's actually no neutral connected up to here. And you might wonder, well, why would we possibly do here the delta connection versus the line connection here? Well, we're still going to get this idea here where if we have a line voltage, the line voltage is equal to the square root of 3 times whatever these voltage sources are. So this VP here, and at an angle of 0 degrees, we'll assume it's in the ABC configuration, VP, and an angle of negative 240. So we still have these line voltages here, square root of 3 VP. But we should remember here that this line voltage, whatever we're given here, that's basically the magnitude of AB, magnitude of BC, magnitude of CA. But what that means is we've essentially connected these loads up in parallel. Because if you look at this first load here, let's look at this load here. This A is connected to this A, and this B is connected to this B. So it's in parallel to this voltage VAB. And so if we're wanting to talk about this current here, which we'll call IAB, capital, because we say, well, it's starting at I'm starting at A going to B. Well, in this case, we get that VAB, sorry, not VAB, yeah, IAB, I wrote it down right, I said it wrong. IAB is equal to little VAB over the impedance. And then we can compute IBC by VBC over ZP, and ICA VCA over ZP. And you might say, well, how is this an advantage to me here? Well, the difference here is that you're actually getting the line voltage getting applied to the load as opposed to the A to N voltage here. So the line voltage is really what's getting applied across here, because remember, this line voltage is the magnitude of VAB, magnitude of VBC, and magnitude of VCA. So we're really getting this line voltage applied to each of these loads as opposed to this voltage source. So we're getting a little bit more voltage applied to those. And then if we want to here, we can go ahead and figure out just using a nodal analysis, like if I want to figure out what I little a capital A is, we can see just doing a nodal here, well, This is I little a capital A. That's coming in here. And if I draw all of these other currents in here, this is I BC, and this is ICA. So you'd have I little a big A plus ICA is equal to IAB. So I little a is equal to IAB minus ICA. And you can come up with the same way for all of these as far as finding IBB and ICC. Same kind of idea. You just have to write different equations down. For instance, let's go ahead and write them down. IBB would equal IBC minus IAB. And then ICC would be ICA minus IBC. And that's just doing KCL at all of those nodes. But then if we want to talk about the line current here, the line current in magnitude is actually equal, of course, to these IAA, I little bb, because I mean that's exactly what these are. These are line currents that we computed. And we also have, if we were wanting to think about these as some kind of IP, we would get here that IL, the line current, is equal to the square root of 3 times IP, which are the phase currents. Alright, so kind of a lot of equations there. A lot of the textbooks will summarize all of these equations here, but there's really not much else going on. We just have more formulas, and we have to be careful on which set of formulas to use on whether I'm a YY connection or a Y delta connection. So let's look at an example here of this. Let me pause it and I'll write up the example. So we're going to do an example here, and actually this example should look pretty familiar with us because it's the same example we did, except in this case we're looking at a delta connected load as opposed to a Y connected load. So we want to determine the amplitude of the line current in a three-phase system, line voltage, to a delta connected lagging at a power factor of 0.8. And so we have on a phase voltage here, so our line voltage is 300 volts. Our phase voltage is 300 square root of 3. And the power factor is still 0.8. But then we still have here that the power per phase is equal to VL IL over the square root of 3 cosine of theta. So we know that power per phase here is 400 watts, And so we get 400 watts is equal to 300 divided by the square root of 3 times my line current, not cosine of theta. We know what cosine of theta is. It's 0.8. And we'll see here that, well, not too surprising, we get the line current to be 2.9 amps. And then if we look at the impedance here, we would still have my voltage divided by my current, which is going to be 300 divided by the square root of 3 over 2.89, which gets me 60 ohms again. So the reason I did this example over again is we can see that, even with the delta connection, we're essentially getting the same answer down. It's just a different way of connecting up our loads. But even with the same line voltage and the same power factor and the same voltage power being absorbed, the load is still the same, 60 ohm, and we get our line currents to still be 2.89 amps.